Oke, baik. Selamat pagi Bapak Ibu, rekan-rekan engineer yang saya hormati. Selamat bergabung. Senang sekali ya bisa berjumpa lagi dengan Bapak Ibu dan rekan-rekan semua. Salam sehat dan mudah-mudahan selalu bersemangat semua. Nah, pagi ini kebetulan saya berkesempatan menjadi moderator dalam acara webinar yang sebetulnya ini merupakan bagian pertama dari joint webinar series antara Windtech dan HAKI dengan topik pengaruh angin terhadap bangunan gedung. Nah, eh, webinar bagian pertama yang dilangsungkan hari ini itu berhubungan dengan wind tunnel testing untuk bangunan gedung tinggi. Sementara nanti webinar bagian kedua itu akan diadakan tanggal 25 Juni di jadwal hari dan waktu yang sama. Dan ini akan membahas tinjauan pengaruh angin untuk struktur atap stadium dan juga struktur atap bentang panjang lainnya. Nah, tentunya ini merupakan topik yang penting dan menarik. Mudah-mudahan seri webinar ini bisa memberi pembelajaran yang bermanfaat bagi kita semua. Nah, jadi langsung saja selanjutnya izinkan saya memperkenalkan pembicara kita hari ini, Dr. Tony Rofail. Dr. Tony has over 33 years combined experience as both researcher and consultant in wind engineering, including 30 years with Windtech Consultants, a global consulting firm specializing in the study of wind effects and sustainable design. Dr. Tony is one of Windtech's founding directors and has been with the firm since its establishment in 1991. His research includes reliability of wind tunnel studies, interference excitation of tall buildings, analysis techniques to accurately determine the effects of coupled nodes and rigidly linked substructures, as well as wind noise in buildings, natural ventilation, and review of assessment criteria for pedestrian comfort. So, without further ado, let us give our full attention to Dr. Tony Rofail and join me in welcoming him. Dr. Tony.
Thank you, Nick. Can everyone see my screen?
Yes, yes.
Okay, thank you. Okay, thanks for the introduction and thanks for the opportunity to present on wind engineering for tall buildings. I hope that this presentation will provide very useful information to all of the attendees. This is a brief outline of my presentation. So I will start with the applicability of the Indonesian standard and at which point you would be directed to undertake a wind tunnel study as a requirement of the Indonesian standard. Also, when is it feasible to actually do a wind tunnel study? Just from a cost-benefit point of view, which is important for development managers to understand. Also, I will cover, as I discuss the key studies undertaken for tall buildings, I'll outline what are the very basic requirements to look out for when a wind tunnel study is undertaken. It's important as a user of wind engineering consulting to have some basic knowledge of what are the minimum requirements. Also, I'll cover a number of case studies highlighting some very useful features in the building forms that have helped these buildings to perform very efficiently in an aerodynamic sense. And then I will outline the three main methods used to undertake wind tunnel tests for structural response, and which method is most suited to what type of structure. And then I'll discuss different methods of combining the wind tunnel aerodynamic coefficients with the climate model and the effect of the different methods on accuracy and structural efficiency. Then I'll touch on a very important subject, which is the interference excitation of tall buildings, meaning how the surrounding buildings can influence the dynamic behavior of a tall building. And when can we expect that to be more pronounced, and some tips on how to manage this situation. And then the next point we'll cover very briefly on monitoring of the motion of tall buildings, which is very useful especially for long-term monitoring. It's very useful as a structural health monitoring tool. And I would consider that to be essential if you happen to incorporate a damper in your building. And I'll explain a little bit on that. And finally, I will introduce two other types of studies that I would say are very helpful in the design of tall buildings. This is the study of surface pressures, or design pressures for cladding and facades, and also wind studies for environmental comfort for outdoor spaces within and around the development. Okay, so that's the, so this should take roughly 90 minutes or thereabouts, and then there'll be opportunity for questions after that. Okay, so we'll start with the first item. Let me just, maybe I'll click on this. Okay, so the Indonesian standard sets out different methods. One of these methods include wind tunnel testing procedure. Okay, and this is if you can refer to chapter 26 of the Indian standard for those details. Okay, but this wind tunnel study is considered carries the same weight as using the Indonesian standard. Okay, so and if it's undertaken, must supersede the Indonesian standard up to a certain limit. So if the wind tunnel results provide loads that are less than 80% of the estimates in the Indonesian standard, then the 80% of the design loads become the lower bound value. So it must be not less than that. Now, a lot of structural engineers correctly state that seismic design generally governs over wind design in Indonesia. And that is very much true, especially with regards to design for strength. However, equally important to the design for strength is design for serviceability and for occupant comfort due to building motion. And in that context, I would recommend these effects be studied in the wind tunnel for buildings taller than 100 meters, roughly. For towers above about 200 meters in height, it is possible that, depending on the shape and so on, and slenderness, it is possible that the wind loads can also govern for strength. Okay, it's not, it may or may not, depending on the actual form of the tower. Okay, but we should not lose sight of the serviceability aspect of the design. Okay. Okay, other Another aspect of wind tunnel testing, which I will cover towards the end of my presentation, which has been proven to be a very important part of value engineering for the building design, is a study of the facade design pressures. So on average, from my experience and getting feedback from my clients, on average, there's a 12% saving in the facade package simply by undertaking a wind tunnel study, and that's on average. So in some cases, it could be a lot more than that, especially if it's in a high dense area, a lot of shielding. If the building is much taller than the surrounds and exposed, you might get at least a few percent saving. But if you do the sums or the maths, even a few percent saving can pay for the wind tunnel study, 20, 30 times. So it's definitely a worthwhile exercise. And as a rule of thumb, I would recommend it for all buildings with more than 5,000 square meter of facade area or more than 70 meters in height. So almost guaranteed that you will get many times the cost of the study back in terms of savings, because of the nature of codes needing to be somewhat conservative to cover any unexpected or unusual cases. On top of that, wind tunnel testing is a very good means of quality control in the design because it allocates the materials where they are most needed and to the correct extent of those hotspots. So it defines those hotspots much more accurately than the code. Okay, so so it's more peace of mind as well as cost saving. Now the section 27.1.3 does state that there are limitations in the use of the standard, like any other standard. There are limits to the applicability. And I've underlined the important part of that phrase: buildings that have unusual shapes or unusual response characteristics. Okay, so if you are designing a building that falls in either of those two categories, then you are required to undertake a wind tunnel study, okay, for wind. Okay, so if a unusual dynamic response could include cases where the design loads are governed by crosswind response, where the standard does not actually cover that case. And as a rule of thumb, this case can occur where the height over width ratio exceeds 5. So basically for the more slender towers. And again, buildings taller than, say, 150 meters, you could get crosswind governing based on the Indonesian climate. So just keep those two things in mind. Okay, and obviously I don't need to explain unusual shapes. Anything that departs significantly from a rectangular shape or or regular shape, then would need to look at wind tunnel modeling. Okay, so I've covered cases basically to expand a bit on the crosswind response. There's a very good guide in the Hong Kong Code of Practice. Says that buildings height over 100 meters in Hong Kong, but that's in the Hong Kong climate. So that I translate that to be over 150 meters in Indonesia. Okay, and they specify height over width for the smallest overall plan width. Where that exceeds 7, okay, so I would say 7 or over 5 or 7, something in that range would potentially trigger a case where the crosswind response would govern, and which is not really accounted for in the Indonesian wind code. So if the above is true, but the fundamental frequency is higher than 0.5 hertz, then you don't have to worry about that. Okay. But if it is lower than 0.5 hertz and it satisfies the above, then a wind tunnel study is required. Okay, so we need to just cover off some important aspects which I covered at the beginning, and that is irrespective of what the loads come out from the wind tunnel study, they must not be, or the loads must not be less than 80% of the design loads stipulated in the Indonesian standard. Okay, next point. Actually, this I'll cover this later, but another limitation of the Indonesian standard, or all standards really, perhaps with the exception of the Indian standard, is that there is no provision for cases where there is an interference excitation. So what does that mean? So if you look at this cylinder in the foreground, so we're looking top down on a wind tunnel floor test section. The wind is coming from the bottom of the page to the top, and we have a cylindrical form in front of the wind. Behind it is another cylinder. Now, what you're seeing here is a time-lapse photograph of both cylinders. And you can see here the front cylinder is oscillating, but very slightly. You can see there's a bit of a blur on the side here. But it causes a vortex. There's a vortex created behind it. And that vortex interacting with a cylinder of the same diameter downstream really amplifies the dynamic part of the response of this downstream building. So if you're designing this building and basing it on the code won't account for this effect. Okay, so, and I will cover a little bit of, give you some rule of thumb as to when this case is likely to occur. So I'll give you some fairly robust ways to sort of assess that. All right, okay, so keep in mind that the dynamic response can increase by up to 50% in situations like that. So if your loads are slightly lower than, wind loads are slightly lower than seismic loads, it may actually push it to exceed seismic loads. So just be aware of that. Now I'll cover a little bit of background on what is a wind tunnel study. Okay, so a wind tunnel, this is a diagram of one of Windtech's 3 wind tunnels. So we have 3 wind tunnels under one big roof here in one building in Sydney. The purpose of the wind tunnel is to generate a flow pattern that simulates the behavior of the real wind down to the same scale as our model. So this disc here in the foreground is a turntable which rotates to simulate wind coming from different angles of attack. In the center, you may see there's a little yellow building, that's our study building. And it's very important to include the surrounding buildings up to about 400 meters radius. Why is that important? It's because of the effect I just mentioned earlier, and that's the interference excitation. So based on the research I undertook in the late 1980s, I have found that going past about 400 meters, buildings don't generate that much of an influence in terms of interference effects. And hence, it is sufficient to incorporate the effect of the building morphology around the site only up to that kind of extent. Beyond that radius, it's still very important to match the same behavior of the wind as it approaches the precinct, okay, and to the right scale. So what are the factors that tell us that we are matching this profile very well? So so before I go into that, I have to explain that sometimes this is not a very simple task, just assessing what is that terrain upstream. And very often you see, a combination of, flat terrain or suburban terrain, water body, flat terrain. All of these have very different flow characteristics. So we undertake a fairly detailed modeling to see what is the combined effect of all of these as they approach the edge of our turntable, which is that smaller circle. And then that combined effect is what we model in the wind tunnel. And that's done for, obviously it's different for different directions. So not only does the wind speed at the site change with direction based on the wind climate, but also is influenced by the upstream terrain. So all of these have to be factored in when we're modeling it in the wind tunnel. Another factor is if the site is very close to a significant mountain or hill, that can also distort the flow significantly. As a rule of thumb, if the peak of the mountain to the site, if the height difference is more than 10% of the distance away from the peak of the mountain to the site, that would indicate that the effect can be significant, and it's really advisable that this effect is actually quantified using this type of study, which we call a topographic study. And this doesn't happen very often in Indonesia, but it may. But this is just for your information. Now, how do we model once we know what is the upstream terrain, how to model it in the wind tunnel? So what we do is we know what is the target profile from full-scale data. So the full-scale data is represented by the solid line. So this here is, in this section here, that's the turbulence intensity, which is the standard deviation of the wind speed divided by the mean value. And this is the normalized wind speed. So it's actually, we choose a reference, it doesn't matter at what height, and we divide the wind speed at different heights by this value at that reference height. In this case, we've chosen 500 meters as our reference height. But that shape has to match between the model and the full scale, okay? And same with the turbulence intensity, okay? So these are the two most important parameters, and these help us to ensure that we're matching that at the correct scale in the model. Another important factor is the spectral density. So if you take the wind speed and you apply a fast Fourier transform to see where the energy is concentrated at what frequency, then what we actually measure that in the wind tunnel, which is the blue dots, we match it to a best curve and see how this best curve fit matches with a target for the scale and terrain, and the offset or the value has to be very close, within a factor of 3. Okay, so that's another, and this is an important consideration because it helps us to match the size of the eddies in the wind, like the wakes of the as they approach our site. So they need to be of a similar size as the real wind. Okay. Okay. The study model within the surrounds should incorporate any other, not just the surrounding buildings, but any topographic effects, such as this small section of hill you can see in the background. Now, blockage is a very important consideration. So the wind tunnel cross-section versus the cross-section of the model at any point along the cross-section of our surrounds, that cross-section must not be more than 10% of the cross-section of the wind tunnel. If it does exceed that, then there will tend to be a speed up of wind around the model, which could exaggerate the effect of the wind, which is what we don't want to happen. Now, in this particular wind tunnel, this is one of our 3 wind tunnels. It's got a what we call a blockage tolerant test section. So it's got this open plenum behind this slatted or partly porous ceiling. And what it does is sort of lets some of the air to seep into this plenum and back out. And tests that we've done with this design allow us to increase the blockage up to about 17% if we need to. Okay. But the model you see at the moment is already less than 10%. So. Okay, and finally, but not a small factor, but a very important factor is the speed in the wind tunnel must be high enough. Okay, the speed in the wind tunnel and the scale or size of the model needs to be, the combination of those two contribute to something called the Reynolds number. So this is the Reynolds number here. So the mean wind speed at the building height times the characteristic cross-section width of the building divided by this constant, which is the viscosity constant of air, must be larger than a certain minimum value to ensure that the flow regime around our building matches the real world. And you can see here, for different Reynolds number, you can see different flow regimes. And that's different for circular shaped cross sections compared to square or sharp edge. For sharp edges, they're not as sensitive to this effect as circular cross sections. Okay, so they need to be particularly high for circular cross sections to match full scale. All right. Now, what are the typical outputs we get from a structural load study? Okay, first, I mean, at Windtech, we provide firstly a headline overturning base moment about the translational axes and the torsional mode here, and compared it against a number of standards. Now you will see the ASCE pretty much lines up with the Indonesian standard, okay? And you'll see that if you look at the along wind response, there seems to be a fairly good consistency between different standards. So look at the Australian versus ASCE or Indonesian, British. They're all sort of within about 15% of each other. Okay. Now, if you were to look at the crosswind forces, crosswind response, so look at the Australian prediction for the same, not provided in the ASCE or Indonesian or in the British. ISO, you can see big departure again in the ISO international standard. This sort of goes to illustrate how complex the crosswind response phenomenon is. And it's for that reason that if you do find that crosswind is governing, then you are advised to immediately undertake a wind tunnel study, because it's the only takeaway from using these codes is just to do that check. But I would not base the design on the code estimate if crosswind is governing. Okay, but it's just a check to indicate that you should be moving to a wind tunnel study. And as I mentioned, it's only for a small subset of tall buildings where the height, in the case of Indonesia, is higher than, say, 150 meters. Now, the outputs, which is what the structural consultant really is interested in, is in the form of these point load distributions. So this is for a simple, 23-story building. And you can see here, we're giving you a set of point loads at each floor at a particular location indicated in the report for a long X, Y, and a torsion moment. And these first three columns are applied, all those point loads are applied simultaneously, and that becomes load case 1. You can see load case 2 is different, and there's in total is typically about 32 load cases to be incorporated into the FEA model. So we provide you a spreadsheet with all of these numbers that make it easier for you to import into your model. Okay, so that's the main output, and we give you a different set for the serviceability loads as well. So we give you one set for the ultimate and one for the serviceability. We also provide outputs of the tip acceleration on the sort of the area on the, which is typically at the top of the building near at the area where you would experience the highest acceleration. And we also present a sensitivity study as to how changes to the dynamic properties of the building will affect these numbers. So this circle here is the predicted dynamic properties as provided by the structural engineer. And you can see here, it's sitting in a table or a figure showing how that would change if the natural frequency changes or sort of reduces or increases. Obviously, as you increase the natural frequency, the acceleration response reduces. And the same applies obviously to the ultimate loads and serviceability loads, which is the opposite of what you see with seismic loads. So with seismic loads, if you drop the frequency, the response actually reduces. So for wind, it's the opposite, okay? And that's because for wind, the peak part of the spectrum for wind is sort of in the 0.05 to 0.1 hertz range. Okay, so as you lower the natural frequency of the building, meaning typically when the building becomes taller and taller, the dynamic response becomes more amplified. Whereas with earthquakes, you can get, typically natural frequencies from around, say, 0.3 up to sort of 1 hertz or something like that is the sort of where the energy of your spectrum is. Okay, so basically it goes the other way. All right, so the other thing that we provide you is what happens if there's a change in the estimated mass of the building. So as the mass increases, okay, this is the case here, increased mass, less response. So that's I guess a reduced mass, there's a increased response. Okay, so that's so you can see here, and with the increased mass, how that varies with the natural frequency. So there's a lot of information that we provide, and then all of that is overlaid against different comfort criteria. Now, the one that you really need to pay attention to is this one here. Okay, this is the ISO International Standard 10137, okay, published in 2007 for offices. If it's a residential, it's more stringent. Okay, so that's this black dash line here. Okay, so criteria varies between residential and office, and hotels are somewhere in the middle. Okay, there are other criteria, but the ISO is essentially the one that is pretty much most widely accepted because it's based on all the latest research. Okay, so that's a bit of an overview of the outputs that you get from a structural load study. I'll cover a bit more on the method or how we do those studies later. Okay. Now, before we do that, I'd like to just give you a bit of an overview of some interesting projects that Windtech worked on and how they performed, aerodynamically speaking. Okay, so this tower here is in the Gold Coast, and it's called Q1 Tower. It's still the tallest building in Australia. Now, this building it's got a pointed aspect, and that point is pointing in the direction of southeast. Now, southeast happens to be the most common direction for the Gold Coast, and it's coming over the ocean. So by pointing, having the more aerodynamic shape pointing in that direction, that's a very good approach, and it ensures that you have a very efficient structure. The other feature, which you may be able to see, is there's a bit of a step out here. It's just a small couple of meters on both sides, and that step out stops near the top, and it's like a double stepped kind of change in the cross-sectional width. Now, by changing that by those few percent over the height of the building, you are avoiding the generation of a large vortex that could form over a large part of the side of a building. So when the building hits a building, when the wind hits a building, it creates vortices. These vortices are like large suction pressure pockets. And the more you can reduce those pockets by shaping the building, the lower the loads. Okay, so and these pockets are generated at a certain frequency, which is a function of the width of the building. By changing the width slightly, you're actually varying that frequency, and so you're reducing the potential size. Now, this feature alone can result in approximately 50% reduction in your crosswind response. That's a massive cost saving. So this building was built. Loads were actually fairly low for the height of this building. Certainly no issues with accelerations as well. Another interesting building that we worked on is Ocean Heights in Dubai Marina. This building has a twist, like a 60-degree twist from base to top. What does that do? It essentially has the same philosophy in by twisting the building shape, the width, the effective projected width of the building relative to the wind changes slightly. And that has the same effect. So again, we see fairly significant reductions. And in fact, we found the base moments on this tower, which is just slightly lower in height to this, very similar design wind speeds, were even slightly less than what we saw in Q1. Okay, so this is another form of tapering. This is index tower, but that's it's not a step tapering, but still tapering nevertheless, still very effective. Another approach that we found is actually very effective in improving aerodynamic efficiency is where you have two slender tower forms rigidly connected at high elevation. And what that does is, and in fact, in 2007, Windtech published, which is still currently the best method or most accurate method to assess the effect of this case, which is the substructure analysis method. And what tends to happen with these linked structures is the peak response or peak action of wind on these two hardly ever happens at the same instant. So if you imagine the wind forces peaking on this tower, but not on this one, what happens? This tower acts as like a buttress. to support the other one. So you essentially got a much better ratio of resistance versus wind load in a situation like that. And vice versa, when it peaks on this tower, that tower is providing some support. And what we tend to see is that the dynamic response tends to come down for these type of structures. And we've done analysis for so many link structures. Not one of these has ever had an acceleration problem. And keep in mind the height of these buildings. This building has been built a number of years ago. It's a 340-meter high tower and had no issue whatsoever. On the other hand, if we were to ignore the effect of this rigid link, there would have been very serious impacts in terms of acceleration response and dynamic response of these two towers. So you could see the effect this system has. So that could be one way of providing an efficient tower form. Another form, this is in India, in Kolkata, is to have recessed corners. That tends to be not quite as effective as the measures I mentioned before, but it provides some benefit. And we could understand that the stepping may not be feasible in every site, especially if it's a limited size plot of land. But the corner treatment tends to produce roughly a 20%, 15-20% reduction in the dynamic response. However, because of the slenderness of this tower, we still had an issue with the acceleration response. So there was an exceedance of acceleration response in this particular case. And we designed and commissioned a damper near the top of this building, which is, you can see here in this rendering. Now this tank is it's actually a stacked tank. So you have two tanks stacked within that same level. And they are designed to be tuned to dampen the motion in both the X and Y, in the two translational modes. So it's tuned to both. Each of those is tuned to both of the frequencies. So it's a very efficient way to counteract motion in two directions. And given that this building needed to have a water tank for fire, as a fire hydrant tank anyway, you could consider the cost as negligible. The overall cost on the project is negligible, because there's no issue, having these tanks double up as a fire hydrant. So the risk of, discomfort due to wind against a fire event is virtually a non-event. The risk is very low. We generally wouldn't recommend that if the tank is there to mitigate, to reduce, say, a crosswind response. And if that's the case, it would be mandatory to have a monitoring system for the water level and for buildings' dynamic properties throughout the life of the building, if that is the case. And I'll give you an example of that. All right. This is an interesting case where it's the reverse. We have actually a layout of buildings where it can increase the response because of the layout of the building. So you have, when you have a line of buildings like that, the last building tends to get higher than normal drag forces due to wind. And these are kinds of arrangements that codes are not really designed for. So just be wary of that. These are some other examples of buildings that we worked on. This is another example of a complex building structure. So there's actually a lift core that takes people up to, I think this, just the level of the neck, I think. And there's a viewing deck up here. We also looked at the loads on this trident structure because of what I mentioned earlier regarding Reynolds number, which is accuracy of flow regime, we had to test the loads on this trident using a larger scale. And just below there is a force balance to measure the forces on this. It's very important to have included the rest of the building because that definitely does impact the loads on the trident. So other outputs in this particular example were the facade pressures, certainly way beyond the scope of codes to look at cladding pressures on structures as complex as this. Okay, so basically for structural load studies, there are three methods that we can use. There's the method called the high frequency force balance method, and that's putting something like a very sensitive load cell inside the building that can directly measure the dynamic forces acting on the building. And there's a pressure integration method where you need to sample the pressures on the entire envelope of the building simultaneously, and that's very, very important. It's all simultaneously with no phase lag, and then derive from that the dynamic response. Now, for the first two methods, we only need to know the dynamic action of wind on the structure. We are not simulating the behavior of the structure in the wind tunnel. That's done mathematically. So we take a time series of the load and then we apply a modification to that time series to account for the dynamic behavior of the building. And that's done normally in the frequency domain. And then we arrive at a total response, total dynamic response that includes both the dynamic action of the wind on the building and the additional dynamic response due to the actual response of the building as well. Okay. So so what you can simulate that with is if you were pushing someone on a swing, if you're pushing your child on a swing and the swing has a natural frequency of sway, the rate of you pushing the child has a big impact on the overall amplitude of movement of the swing. So the relationship between the rate of pushing of the child, which is the wind action itself, is actually what we're measuring here. And the effect of the natural frequency of the sway is done mathematically. Okay, so that's done in this. Now for the third method, we do everything in the wind tunnel. Okay, so we simulate the natural frequency, the mass, the sort of the building, or the structural density of the building, the damping, etc. It's all done in the model, and so we end up with the final result in the same result. So each of them has their advantages. So with the first two methods, they're quicker, cheaper, but also far more accurate in replicating the dynamic properties predicted in the structural engineer's finite element model. With the aeroelastic model, you can imagine that there needs to be some level of simplification, and normally the best we can do with these is just model the relative stiffness of the building in the two sway modes. Okay, so that's now luckily the torsion response does not incorporate any effects of aerodynamic damping. So it's been demonstrated that the sway modes are the ones that you need to look out for. But why is aeroelastic model important? It's important for the cases where aerodynamic damping is critical. So what is aerodynamic damping? That's when the motion of the building can increase or decrease its dynamic response. Now, this doesn't happen for a vast majority of buildings. It's only for the very tall, very slender buildings certainly in Indonesia, you'd have to be sort of over 350 meters in height for a tower to have a likelihood of having an aeroelastic effect or aerodynamic damping effects. Okay, this could happen obviously at lower heights in more severe climates like Hong Kong. You know, it could happen for less than 300 or 250 meters height. It all depends on, so we're working on a project in Hong Kong right now, which is just a bit over 200 meters, but it's very slender and hence it's needing an aeroelastic model. Okay, so it's, and I'll explain to you how to assess for yourself if you need to go to an aeroelastic model. It costs about twice as much as the others, but that's not, it's not the cost is the issue, is if you can demonstrate, if we can tell you or confirm to you that aerodynamic damping is not an issue, you're better off in terms of accuracy as well to go with this. And I'll explain to you why. Okay, so start with the first of the three methods, that's the force balance. The force balance has one limitation, actually maybe two main limitations. First limitation is we need to make sure the model is super light and stiff, because when you take a load spectrum from this force balance, and I'll show you what I mean in a minute, the model itself has its own natural frequency. And you want to make sure that natural frequency is high enough so that it's not in the area that would be of interest for our analysis. And I'll explain in the next slide. But the other limitation is we don't have information on how the mean component of response distributes with height. Okay, so we tend to estimate that based on code distributions. So from the force balance, we obtain the overall standard deviation and mean response. Now, the standard deviation response is expressed also in a spectrum. So these are for each of the 36 wind directions. So it's very important that these structural load studies and pressure studies are done for 36 wind directions. Okay, it should not be less than that. Okay, so you've got the response. So this is the reduced frequency, and that's the magnitude of the response. And you can see here, based on the dynamic properties provided to us, the ranges of reduced frequency are in that range. Why they are arranged in a single number, given the building has particular natural frequency for this axis, it's because the designed wind speed, which is part of this normalization, is not uniform with direction. So each wind direction has a different speed. And so that's why for the, that's why for different speeds, you'll be moving at different points on this. But the important thing to note is the model itself has contributed to this little peak here. So that needs to be, I guess, corrected, or we tend to account for that, or basically correct the effect of the model. But if this happened to be in here, meaning the model is not as stiff, it's lower frequency, then we have a problem. Okay, so that's very important to make sure the model is light and stiff. The second method for looking at structural loads is using a pressure integration method. So we have pressure taps all over the building, and then each pressure tap represents a certain area on the building facade. If you multiply the pressure on that point by the area, you get a force. So that force acting in a particular direction will create a certain base moment about X, Y, and Z. Okay, so including torsion. So by integrating the effect of all of these taps on the base moments, you can get a time series of the base moments. So that's essentially how this method works. Now, it's very important, though, that you have a high quality pressure measurement system that does not introduce any lag between the first and say 500th channel, for example. Typically you can have 400, 500, since they all have to be able to be sampled within like 30 degrees meaning 1/12 of a cycle, of a pressure cycle, okay? Which is a very fast, very, very precise method, okay? Now, the advantage of this method is that we have very good information on how the mean component of response, which in many cases accounts for half of the peak response, we're able to know how that distributes accurately in the building. So and the other advantage of this method is we could actually utilize the same data set to determine the facade cladding pressures without having to do a separate wind tunnel test. So there's actually a cost benefit as well. Now for the third method for structural response, that's the aeroelastic, okay? As I mentioned before, this method is not needed except for perhaps less than 5% of tall buildings, and they're very tall and very slender buildings, okay? Now the ratio of the building's stiffness in the X and Y sway modes needs to be correct to within 20%, okay? Also, the mode shape needs to be correct as well to within 20%, okay? We also, at Windtech, we go beyond that. This is based on the Quality Assurance Manual, the Australasian Wind Engineering Society Quality Assurance Manual, where I was actually one of the key authors. But I wasn't able to convince the rest of the committee to put the other requirements, but that's a minimum requirement at Windtech to also add the structural density, mass distribution, structural damping also matched in the model. Okay. Okay, so when do we know that you need to do an aeroelastic study, okay, over a force balance or pressure integration? And the key to it is working out the reduced velocity, the design reduced velocity of your building. So how do we do that? That's a very simple expression. So you will first establish what is the reference mean wind speed at the building height. And that's basically, you can actually take the gust wind speed in your code, apply the terrain and height correction, and then apply roughly a factor of 0.6, say it's 0.66 to that, and they'll give you a rough estimate of the mean value, okay? Then you divide by the estimated natural frequency as a product of the minimum overall width. If that product, if this expression is below 8, then you don't need to do an aeroelastic study. If the natural frequency is so low, or width is very low, or the building is in a very high wind region and tall enough to result in this being 8 or greater, then that's when you should be thinking of doing an aeroelastic study. In fact, it's highly recommended. Now that number becomes lower for other shapes. So if it's hexagonal or octagonal shapes, that issue kicks in at numbers of 6. Now for circular elliptical plans, it's from 4, which is why you don't see many super tall buildings with that kind of cross section. Okay, so just to sum up, basically the pressure integration and force balance are better equipped to deal with sort of complex dynamic properties such as coupled modes and other complexities, okay? But for those very small percentage of cases where you are to exceed these, you also recommended to do an aeroelastic model study. Now, Windtech, we tend to do both, okay? That's why some other consultants do both for the same prices. to do just the aeroelastic for the same price that we do both methods. Okay, and I'll explain to you why doing both is actually much better. Okay, so firstly, this is just a video showing an aeroelastic model in wind tunnel. You'll see the model is actually oscillating in the wind, and it's all of the dynamic properties are modeled correctly in this model. So I'll just play that again. Okay, so that's exactly how the actual real building would behave in an extreme wind event. Okay, that's in this case a 1 in 50 year wind event. Okay. Now what happens? I'll just move ahead with this example, and in this example we did a HFFB force balance study as well as an aeroelastic study. Okay, which is what we at Windtech we always like to use this hybrid method, and I'll explain why that's so much better than just using the aeroelastic. So, so when we do that, we overlay the results from both methods on the same graph. So this is for moments about X, this is moments about Y here. Okay, the two translational modes. You can see that they collapse quite well. You should be able to see that the means collapse exactly as well, because there should be no reason why they don't. Now in the maximum and the minimum values, there you notice that there's a departure with the aeroelastic. So you can see the aeroelastic has an increased response from these angles of attack here, okay, which is roughly east or southeast direction. Okay, but for other angles of attack, you don't see much of a change. What that tells us is that aerodynamic damping effects for these angles of attack is negative damping, meaning that it actually takes away from the structural damping. Okay, and by doing that, the response increases. Okay, luckily in this case, the angles of attack were not governing the design, and the angles that did govern, which are these ones and those ones, were not affected by aerodynamic damping. Okay, and this angle of attack is when basically the wind is hitting the narrow face. Okay, when you see wind hitting the narrow face, that's where you tend to see the increased response. Wind hitting the wide face, you tend to see the opposite. You can see some reduction. Okay, so that's called positive damping. So what we tend to see is we tend to see with aero elastic model tests that for the cases where there's positive damping, meaning it's the wind is having the effect of adding to the structural damping because of the actual motion of the tower and the wind, they tend to actually occur in the directions that really affect the design. So overall, we're seeing roughly a 20% reduction in the base moments about this axis. So generally, it's beneficial to do an aeroelastic study. Certainly worthwhile from that point of view. So if we do identify that aerodynamic damping is likely to be significant, we highly recommend that it's done. It's good because otherwise you could overestimate your base moments. Sometimes could lead to recommendations for a damper, which may not actually be needed if we did account for the aerodynamic damping effects. And for cases where you have an oval or circular cross section, you may find that even in serviceability loads, you could actually be you will tend to under design. So it's the opposite. You tend to actually have negative damping effects for these shapes. So be very careful with that. Okay. So the motion in the wind tends to amplify the response. Generally not recommended for very tall buildings for that reason. Okay. Similarly for the hexagonal and octagonal shapes. So, so basically square rectangular shapes are generally preferred for very tall buildings for that reason. Okay. All right. So as I mentioned, we tend to get 20 to 30% reduction for the square rectangular shapes, but not necessarily the sort of the opposite is potentially true for other shapes. This is another example. Now, this example is for this actual model here in Australia. So this is somewhere in Melbourne. Very slender, tall, roughly square-shaped building in plan. And you could see here in the ultimate loads, the ignoring aerodynamic damping, it's the dashed line. With aerodynamic damping, you can see there's roughly a 20% reduction in. So overall, we're within a base moment coefficient of 1.5 compared to sort of 1.9. It's a big saving for the client. Okay. Now for serviceability, it actually goes even higher. So we actually found that for the serviceability loads, we were getting about a 30 to 25% lower serviceability loads. So you could see here from this, this is basically research done at the University of Western Ontario in Canada by Professor Vickery. You can see here this beta is actually not aerodynamic damping. It's actually a function of aerodynamic damping. But you could see that this beta factor becomes in positive territory beyond 8, okay, for that mechanism, for the crosswind response for wind normal. Whereas in the other direction, where we don't see a reduction, it doesn't tend to be positive, okay, and I'll show you the similar work done by University of Western Ontario. But as I mentioned in the other case, for the critical directions, you don't tend to see a increase, okay? That the increase tends to be more for the, so that's the aerodynamic damping, virtually no effect, because it tends to govern in the less critical directions, okay? So, so even here, there's a bit of a reduction, but overall, it's this side that's governing anyway, and not much of a difference, okay? And you can see here that this looks like a big number, but it's actually not. That's not the aerodynamic damping. It's the value is more like the 0.2, so roughly 0.2% when you convert it to damping in this case. So so it's the direction where you see the biggest effect is when it's actually hitting the narrowest face. Okay, now this is an example of a project in Sydney, a very slender building in Sydney CBD. We tendered for this, and the tender was correct. It had the right scope. You need to do an aeroelastic study. We lost this on price because the winning tenderer didn't include an aeroelastic study. They only did a force balance. But what happened is we found out later that the loads were very difficult to manage by the structural consultant, and eventually the site was sold out, was sold to another developer. But it just goes to show you how sensitive it is. These sort of tall slender buildings are to wind, and how using the correct technique is very important for the viability of the project. Other issues with this building form is the fact that it's a uniform shape all the way to the top. So not the most aerodynamic form you can achieve for a height like that and slenderness. Okay, so next topic is once we obtain the wind tunnel results, you will notice I presented some of the results earlier in terms of coefficients, because that's really what you get out of the wind tunnel. But to convert those coefficients into actual base moments in meganewton meters, we need to combine them with the wind climate data, okay? So there is no single method used by various wind consultants in that regard. The most common method is using direction multipliers and using what we call the sector method. Okay, and then seeing which direction creates the largest combination of velocity, pressure, and aerodynamic coefficients, and then design to that. So this method isn't a bad method. It's actually quite good, but it tends to be a bit conservative. At Windtech, we tend to use the full climate model. So this rotating graph here shows probability of wind speed. So the vertical axis is probability. The radial axis is the magnitude of wind speed. So obviously the higher the wind speed, the probability of that comes down. But that also changes with direction. Okay, so we use all of that data. We don't actually simplify it in any way. By using the full data set, this is what we call a performance-based approach. It's a lot more computationally intensive than the method I just explained earlier, using direction multipliers. Okay, but it is far more accurate, and as a result, it does take out a lot of the over-design. And I'll show you in the next couple of slides. So just to recap, there's a direction multiplier or sector method. The multi-sector method, which is a method that we have been using for the last decade or so. Prior to that, we had been also using the sector method or direction multiplier method. There's the outcrossing method, which is used by most Canadian consultants. And I'll explain to you that this method is actually not suited for the Indonesian wind climate. Okay, not suited for climates that are governed by thunderstorm events. Okay, because they tend to significantly exaggerate the accelerations, and they tend to potentially underestimate the ultimate loads. Then there's the storm passage method or the load effects method. This method is essentially the gold standard because it's essentially monitors the base moments from each windstorm and does a probabilistic analysis of that. The problem with this method is if you were to determine, say, a 50-year event, 50-year return, the resolution becomes very poor because we don't have climate data that goes, for hundreds of years, which is what you need to get, reasonable resolution on the 50-year event. But I'll show you a couple of slides on how the direction multiplier, like these different methods compare against the storm passage method. Okay, keep in mind that at the higher return or the longer return periods, the storm passage method's resolution is a little bit poor. Okay, so just going back to the direction multiplier method, as I mentioned, it's essentially looking at each wind direction independently. First, establish a design wind speed for each direction using a direction multiplier. That direction multiplier has embedded assumptions in there, which are not always what actually happens in the real world. And that's the main reason why this method tends to be somewhat conservative. But it's still, like, it's used in many codes, and it's not a bad method. And what we do is we obtain, for example, if we're looking at cladding pressures, you obtain the coefficient, aerodynamic coefficient from the wind tunnel, then you multiply it by, say, the velocity pressure here to get a pressure value for that wind direction. And you do that for all the wind directions, and the direction that the maximum direction or pressure from the highest pressure from a given direction becomes your design value. Okay, so that's essentially how this works. Now, with the multi-sector method, we actually, okay, let's go to the outcrossing method. What it does, it's sort of, if you go back to this equation, it says, okay, let's, well, we know this value. let's assume a pressure of say 1 kPa. What would be the corresponding wind speed for different directions? Okay, so that number does, the coefficient obviously changes with direction. But so for a given 1 kPa pressure, that will also change because of the change in here. And so you end up with this locus of basically a wind speed, a corresponding wind speed for a given pressure assumption. Then you run your wind climate data through this and count how many times the wind speed crosses that number for the different directions. Then you change the pressure assumptions from 1 kPa, say, to 1.1, and you repeat the idea, the whole process. In the end, you get, for each direction, you get a number of crossings at different levels of pressure. Then you can determine from that what is a probabilistic assumption for what's a statistical peak for each wind direction. Okay. Now, so this method, one of the main problems with it is it needs to work from a parent distribution. As you can see, it runs, hourly mean data, or hourly mean data through, and based on because the coefficients are based on mean reference wind speeds, and then they need to apply some kind of correction because you need to relate to an extreme event. So that's this method tends to be okay if your extreme wind climate is governed by very long duration windstorm events, known as synoptic winds. Okay, so if it's a thunderstorm governed climate like everywhere in Indonesia, it doesn't work very well. Now for the multi-sector method. Multi-sector method starts off with the same approach as the outcrossing method. We run with say a 1 kPa value, and we look at what for each direction, what is the probability of exceeding that. We sum up the probabilities. The difference here is we don't base it on a parent distribution. We actually have an extreme climate model. So we actually have something that looks like that, but based on monthly extremes. Okay, so we don't need to do this sort of transformation in the end because we obtain these probabilities directly, okay, from this extreme climate model. All right, so that's the real advantage here. So this may sound a bit too technical, but the implications are quite significant. So it's very important for you to understand that sort of this important. So what we do is we iterate through different increments, and this is essentially what happens in our automated process. Sorry, the arrows are in the wrong place, but basically then you can interpolate between these iterations to get, say, for a 50-year return, okay, that's a 50-year, you get the corresponding design pressure, say 1.8, which is what happens here, okay, so which is a 0.02 probability, okay. Now let's just see how they compare, because the results are not always very similar. Okay, so this is looking at work done not by Windtech. This is work published by Dr. John Holmes in 2015, showing comparison between the outcrossing method, which is the blue dots, the storm passage method, okay, which is the dark blue symbols. You can see how sort of the actually resolution is good up until you get into the sort of a value of 4 here means 50-year return, by the way. So 50-year return, 1-year return, you can see there's a bit of a departure by the outcrossing. It tends to be significantly overstating the response. And but you could see that the multi-sector method looks like it. You almost mistake it to be a regression fit for the direct method or the storm passage method. So it just illustrates how accurate this method is. And the multi-sector method, the direction multiplier method tends to be generally conservative. Okay. So what we've done is, we're just going to skip this. Oh yeah, so this is looking at, again, for this particular building that I just showed you, we looked at how the direction multi method compares against the multi-sector method. And you can see here, the symbols represent the storm passage method. And you can see that the resolution starts to fall off at the 50-year return period. So this is 100-year, 50-year, and you can see at the 50-year return period, the simpler method tends to overstate compared to the solid line, which is the multi-sector. Okay, and same with the other points. And this is a scatter plot of all of the pressures against comparing multi-sector and direct method. Very good match. So if it sits on that dashed line, means the values are equal for all of the values. Here we see generally they're all on the right. I mean, that's the safe side of the line. You don't want them on this side at least, but there is some conservatism, as you can see with the direction multiplier method, by on average about 14%. If you draw a line here, you'll see that that's a slope about 1.14. Okay, so I've already introduced interference. Okay, so let's see how we can predict interference. Okay, so when does interference occur? And the answer depends on the following factors. First, the spacing. There needs to be a certain spacing between the buildings. The magnitude of wind speed is a factor, but also the upstream terrain is another factor. And so based on terrain and open terrain, which is fairly basically like a grassy or flat plain, if our study building is located at this point here, and another building of a similar cross-section plan is located, say, in this zone here, we could, based on our research, we can see potentially up to 50% increase in the dynamic response, and up to about 30% in this zone here. Okay, and then very low effects in this zone and in this area here. So this is like typically about 20 or 10%. But the important zone to look out for is obviously this zone here. And the reason is the building located here will create a wake on either side. So this, obviously the mirror to that is true. So it could be either side. That's just telling you how much offset. So it could also be here. All right. So so basically, the wake from the side of the building tends to interact more effectively than if the building is immediately in front. If it does happen to be immediately in front, there's a particular distance that's most critical. Okay. Now, as the upstream terrain is more built up, now this is actually a sort of a suburban terrain, sort of not so dense, but it just needs to be not an open terrain for that zone to really diminish substantially. There is obviously this interesting situation here where the buildings are very close to each other, and there's a mechanism that I suspect is we call a lock-in excitation mechanism between the two. But ignoring this particular spot, again, it's generally in that sort of general zone. The effect is less. And as we go to a sort of a high density urban environment, say in a city environment, the effect is obviously a lot less. Now, keep in mind that this is just with one interfering building. Once you introduce a lot of buildings between the interfering building and the study building, then that really becomes not an issue at all. So, okay, so this is in an area where you have a city center just here, right? And you have a big gap, and then you have this tower, and then you have our study building. Okay, but if both buildings are located within a dense cluster, then you don't have to worry about interference. Because the vortices will be always confused by the other buildings. Now this is probably the most extreme case I've come across. So here the wind's coming from the left side of the page, okay, which is the opposite to what you just saw before. And you could see if there's a point here at the top of the building, that's where the point will actually end oscillating if the building was in isolation. Okay, so you could see the crosswind and the along wind. There's a mean component there, and then you have the dynamic component in the along wind. Crosswind, zero, the mean is obviously zero, but you can see the dynamic can actually be higher, like the peak can actually end up being higher than the along wind peak. And this is for very slender buildings. This is like an aspect ratio of 13 to 1, okay? You don't see that happening that often. In fact, if the building is, say, aspect ratio of 5 to 1, it will always be less than the along wind. For the crosswind, it'll be sort of hovering in that sort of zone here. Okay. Now, but what happened is we found this very unique situation. If we place a building downstream in this particular location relative to the same wind speed, plotted at the same scale, you could see this amplification in the response. Okay, but this only happens for buildings pretty much facing the ocean, same cross section, very close in that particular orientation. So be careful if you're building a two tower project that are very slender buildings on near a waterfront. Just be aware that these issues can occur. Okay, so this is another interesting example. This is a very unusually shaped building in Dubai. Sorry, in Abu Dhabi. That's the building here. Same building, different 3D print process, but it's essentially the same shape. We tested it originally with this very unusual spaceship-looking building nearby, and then the developer of this neighboring building decided to change it to this more elegant design. And what we found is the interference effects caused by this building were quite substantial, but with the new design, suddenly all those effects have diminished. So it was definitely a good idea to repeat the test with the effect of that. So this is the building cross section, quite a slender plan form, and this is the spectrum. So basically, the area underneath this curve is essentially proportional to the square of the dynamic part of the response. So if we look at these wind directions, so this is also, there's 36 curves here for the 36 wind directions, and those two lines represent directions 60 and 70 degrees from north, okay, east of north, and that's essentially where that quad building was. Repeating the test without that building, you can see the effect is pretty much dissipated completely. You can see the effect of wake interference, and this is doing a load ellipse for 36 wind directions for the same results, just to present in a different way. So this is actual base moments in meganewton meters, and you can see the effect of that quad building or spaceship looking building on the crosswind response on this subject tower. Removing that quad building suddenly basically eliminates that effect completely. We saw a similar effect in Sydney, where we saw this building here, which is head and shoulders above other tall buildings in the precinct. The loads typically you'd expect to be 20+% lower than the code. In this case, it was very, very similar to the code. And when we got drilled by the structural consultants to why, we, based on our experience, we said, well, this would have to be the cause, because that building happened to be in upstream in the most predominant direction for the site. We repeated the test without that building, and very much as predicted, we saw. So this is what we told the client, said, well, actually, this interfering building is located here relative to the prevailing wind direction. And based on our estimates, it'll be a 30% increase over if this building wasn't there. And so we repeated the test, and that was exactly what we found. So from that direction, which was the south direction in Sydney, we got a 30% reduction to the response in that about that moment. So these effects are true, are real, and just want to make sure you're aware of this. So I think I'm coming to the end of my time. So I'm just going to skip this other case study. So to sum up, if your building is sitting in a climate like this, like Manhattan, don't worry about it. If it's sitting in an area like that, and perhaps if your building is, say, this one here, and there's another one there, there could be some potential effects, especially if the prevailing wind is the southeast, so that's southeast coming around that way, could create some interesting effects. Okay, on-site measurements. This is something that a service that we offer. In fact, when we did the wind tunnel study for the Gamma Tower in Jakarta, which is currently the tallest building in Jakarta, there was a slight concern of the likelihood of the crosswind response going beyond the seismic design for this building. Okay, this building is 285. Note this, we did talk to them about the inefficient form, but I think the architect preferred to have this nice, clean, straight edges. So, but in the end, they installed a damper just as a precaution, which we designed and commissioned. So because of this damper being positioned to just reduce that crosswind slightly, we installed a long-term monitoring system to monitor the water level in the tank, as well as the dynamic properties of the structure. And this is me just doing some spot measurement at close to topping out of the structure, so we can fine-tune the design of the damper, which is a big U-shaped tank. That's the tank here that's inside this building. And this is the type of gear that we use. It sort of can measure building movement down to micro G level. So 1/1,000,000th of gravity. Okay, keep in mind that criteria for accelerations are measured in 1/1000th of gravity. So it just goes to show you that, we're picking up the slightest movement. If you were to sort of stamp your feet, 20 meters away, it'll pick it up. Okay, so so that's the unit that it currently resides in, and it's all you need. All we needed was basically a PowerPoint and an internet connection, and we are monitoring the building's motion from our office in Sydney, and anyone can monitor it from anywhere in the world with this with the gear that we've put in there. It's also very helpful when a earthquake event occurred at the other end of Indonesia. We managed to pick up the earthquake signature, which is this signal here, and we're able to quantify how many milli-G was actually measured. It wasn't very much, but you could see, we're picking up a signal where the peak is actually 0.05 milli-G, right? It just shows you how accurate. There's no way any of the much cheaper systems could have actually picked up this signature at all. That would be within the noise level of most instrumentation. Okay. And so the system determines the natural frequencies and monitors how they change over time. So it's very important for structural health monitoring. So it's through a spectral analysis, we can monitor the natural frequencies of the first three modes over time. And sort of once we see any step change post an extreme event, that could help the structural consultant identify where the sort of damage has occurred in the structure. All right, so I'm going to skip this because I'm running out of time, but this just shows for facade cladding pressures, how well we're able to match full scale, which is the symbols, against our wind tunnel results. Now, this particular point here is a point that Windtech so far is the only consultant that happened to show a good match against. It's a very difficult point near the roof corner of a building to show this such a good match. So these are the kind of outputs that you get. You get a pressure zones. This is in PSF, obviously, because this is an American project. But you can see here, we're able to highlight the areas that have the highest pressure rather than design all of the corners of the building to this red zone, or even a bit higher than that red zone. We actually, you can achieve quite a big cost saving by focusing on the area that does need that higher pressure and working to sort of the actual expected pressures. And finally, just wanted to just make you aware that another important aspect for tall building design is to look at the effect of the building on the environment for pedestrians and occupants. So not only for pedestrians walking around the site, but also people using communal recreational facilities within the development, and making sure that these don't become uninhabitable because of the strong wind conditions. And if they do experience harsh conditions like that, Windtech are the best placed consultants globally to come up with the most elegant and effective and cost-effective solution, using, fairly sort of architect-friendly suggestions to mitigate. So this is an example of the mitigation strategy for this particular design. And there are so many techniques. So this is a combination of screens. They're orange line and strategic planting. We're happy to work closely with the architects to come up with a solution that's sort of in line with their vision for the project. Okay, so at this point I'll finish and hand over to Nick to field questions.
Okay, Dr. Tony, thank you very much for the interesting presentation. So now let's just go ahead and try to open the floor for questions. And right now I'm actually looking at the Q&A chat space, and there's plenty of questions already. So I'll try to assist you and try to read them off one at a time. I'm not sure if we're going to be able to answer all of them live, but let's give it a try. So first question is by Panin Hudaya, and the question is: effect of surrounding buildings is very important and has significant effect to responsive building to be tested. When we do wind tunnel test for a building, but at that time we do not know what buildings to be built in the future within the radius of 400 meters, then how do you manage this sort of case?
Yeah, it's a good question. Yeah, so what we do at Windtech is if we always put forward a suggestion to the client that we test at least 2 different surrounds cases, even if there is no information on future buildings at the time. Our clients will probably have a better idea than we do as to which sites nearby are likely to be developed in the future. And if they could just let us know that please consider future development in this precinct, we could develop a hypothetical building form that we believe is actually would be potentially a more critical case. So we can take a slightly conservative assumption in terms of the form of a tower in that neighboring site. So it's better to do that than to totally ignore the problem. If you are located already in a dense part of Jakarta, for example, that is not such a big issue, but it is important if you are building a tall building that's in a fairly low density environment, but are aware of a potential development nearby, development precinct, or if your own development is to be staged. So you're going to build one tower and wait for a number of years until the next stage, then it's important that the first stage is tested with and without the future stages.
Okay, thank you. So let's go ahead to the next question by Livy and Teddy, Pak Teddy. So in Indonesia, if the tall building is lower than 100 meters, may I ignore wind load and just consider seismic load in our lateral load building design?
Well, as a wind engineer, I can't just say yes to that question. So you still have to do the checks, I think. But because this building may be, I don't know, 10 meters wide by 100, and you might get some interesting dynamic effects. I don't know. It's always to do some due diligence for your wind load. That's all I could say. And if crosswind is governing, let's have a dialogue and see what the risk is. Just happy to assist. I can't generalize here.
Okay. Next one. I understand that this session talks about high-rise buildings, but what do you think are the requirements for wind analysis for complex and large roofing structures, such as stadiums, airports, stations? When, if ever, are wind tunnel analysis important for this case?
Okay, that's a good question. Now, actually, I'm pleased to inform that on Friday, the 25th of June, Dr. Nicholas Truong from Windtech will be running a session specially to answer this question. But as a rule of thumb, if the span is, say, more than 20 meters in a large roof structure, then it could become quite a dynamic structure in the wind, and we would generally recommend some wind tunnel modeling to be undertaken. Yeah, so that's, or just from a value engineering perspective, if even just big, very large warehouses, very often people who design them come to us to establish, the structural load cases for those, and often the design loads are completely different to what you would have to design to if you were using the wind codes. So, from a risk mitigation point of view for the lightweight long spans, but also from just the regular shaped buildings can benefit also from a value engineering aspect. So keep a lookout for HAKI's announcement. I think HAKI will be announcing this presentation very soon, I believe.
Okay. All right. Thank you. Next one is from Ryan Irnanto. One of the influence results of the wind tunnel test is modeling the atmospheric boundary layer. Could you give your opinion about modeling the atmospheric boundary layer in wind tunnel test?
Okay. Look, this is a very well-established procedure now. And as long as you are following the target profile within plus or minus 10%, you can be comfortable that the results will be accurate. Okay, so this is not an area this is an area that's been a well-established procedure over many years and has been with comparisons between wind tunnel and full-scale measurements undertaken. We're very confident that this is a very robust method to model the boundary layer profile.
Okay.
The big questions is the method of basically the method of measurement of the effect. Okay, it's not the actual modeling the wind; it's how you measure it is very important. There's so many provisos there, and also how you combine the directional multipliers, a directional variation or wind climate model with those measurements.
Okay. And next one here, we have Pak Benjamin, Pak Ben, Lumantana. Question is somewhat related to the first question, actually. Maybe a continue, a follow-up to that. Let's see here. Wind load depends on existing other surrounding buildings. So what happens if we follow the result of the wind tunnel test and later the landscape changes?
You're welcome if you're a building owner and you're concerned. You're welcome to have a dialogue with me, and I could tell you whether it's worth being concerned or not. If we do agree that there may be a concern, and I think we can just look at the effect of that. There are ways to deal with it, such as installing a damper, etc., in your building to reduce dynamic response. So it's not really a huge catastrophe, I guess, but normally over time, as more and more buildings come up, the interference effects hopefully will be less because of the other buildings disturbing the vortex being shed by other future buildings. But just keep in mind the rules of thumb that I presented today, and feel free to contact me if you need some guidance. I think if you have a copy of the presentation, you'll have my email address.
Okay. Next question from Arga Yudhistira. In wind tunnel testing, we know that the geometry of building and the surroundings are scaled, but what about the wind velocity? Is there any similitude law that needs to be fulfilled in order to model the inlet velocity?
Okay, so in the wind tunnel, we measure basically based on similarity in a normalized wind speed. Okay, so normalized. Everything is scaled. So we scale the wind speed. We don't actually. There's no need to model the absolute wind speed in the wind tunnel. Okay. So, for example, if we're looking at the aeroelastic response of a building, we don't model the 1 in 50-year wind speed. We model the reduced velocity that corresponds to a 1 in 50-year. So you take that wind speed divided by the width and natural frequency, gives you a reduced velocity. Those have to match exactly, not the. So what happens is, in this example I just mentioned, the wind speed will be lower in the wind tunnel than the full scale, perhaps half or a third, but that's compensated by a smaller building width. Okay, but the building width is a lot smaller than a half or a third, so we increase the natural frequency, which is also in the denominator, to compensate. So in the end, the goal is to have the same reduced velocity, for example. Okay. And for other types of tests, the aim also may not be just, it can be even less onerous, because you just need to have a high enough Reynolds number. So if the Reynolds number is high enough, then you will model the flow regime correctly around the building.
All right. So the next question by Mr. Roni Hermawan regarding the device of structural health monitoring system that has already been implemented by Windtech so far. Can it also work to monitor seismic effects on a building?
Oh yes, absolutely. The same equipment is able to monitor that, and I think I've shown you an example of the instrumentation picking up a seismic event. So that's certainly can be used for both. Yeah.
Right. And then another one by Mr. Hanky Mulyawan. Please help explain the main difference between fastest mile per hour and the 3-second gust wind speed, and why in the latest code or standard preference is to use the 3-second gust.
Okay. Yeah. All right, the fastest mile per hour is something that was inherited from the American standard. It's not the best measure because it's a very long averaging time. It's essentially what it is. Um, it's a running time average, but not based on time. It's based on distance. So if you look at the distance a wind front travels over a distance of a mile versus the time it took to travel that distance. So it's a little bit of an archaic measure of wind speed. So now we have much more sophisticated instrumentation spread at very high density around various countries around the world. We don't need to do this rough approach. We can measure stuff more accurately using these new instrumentations. So the World Meteorological Organization has established that all airports are to report based on a 3-second gust. So the codes have to follow this approach just for consistency.
All right. The next question from Ibu Prasanti Widyasi. A lot of wind load on tall buildings is related to the geometry of the structure, so perhaps it's best to do aerodynamic analysis and adjustment of the shape of the building with the architectural drawings. Can you explain the procedure at which stages wind engineering inputs are given into the design of the overall structure and whether there are large updates to the final design?
Yes, it doesn't happen often, unfortunately. There's I'd say a minority of architects come to us to provide that kind of input. Okay, just a very small minority. Unfortunately, for most architects, they tend to come to us after the design has been finalized, and so I think it's comes partly from sort of education process where architects need to know the effect that their building form has on the viability of the project and the overall cost. I do know architects who design very tall buildings do this as a compulsory part of the design process. So the large international design firms around the world come to wind consultants such as Windtech and provide initial feedback just through a video conference, and then sometimes they test a number of alternative schemes in the wind tunnel right from the concept design stage. And this is not so important if your building's 200 meters high or less in Indonesia. Once it goes higher than that, it does make a big impact on the cost of the project to do that bit of homework before you lock in the building form.
Okay, so I have another question here also related to cost, actually more on the wind tunnel side by Angin Terhadap. You mentioned the factors that influence the cost to do a wind tunnel of a high-rise building. Any rough cost estimation per square meter to do wind tunnel test for a high-rise? Any
Okay.
minimum cost to do wind tunnel test?
Well, when you think about it, the cost is negligible. The cost of a wind tunnel study. It'll be, I don't know, maybe a couple of cents per square meter. Who knows? It's not a very big cost. Okay, so, we're talking to do a structural and pressure study for a, 200 meter high tower. We're talking maybe less than 30,000 US for if you're doing a very tall building, 400 meters, then there's a bit more cost because you would have to do an aeroelastic study and so on. So it could go up a bit more, maybe 45,000 or something. They're not large costs.
So you're saying it's more related to the complexity of the techniques?
Yeah, it's not per square meter. We don't look at it that way. We look at the height, slenderness ratio, what type of studies needed, how many towers are in development. They're the kind of things we look at the complexity of the structure. If there's two towers with a bridge connection at the top, there's a bit more cost involved to analyze the effect of that rigid connection. If you have a facade that has a double skin facade, that's going to cost more than a simple single skin, because we need to look at loads on both layers of facade, of porous facade, outer skin. There's so many things that if you have sunshade elements, we need to determine the loads on the sunshades. That would be more than if there was no sunshade elements. So there's so many. So once you depart from a simple prism shape, then there will be a bit more work to do. If to do the job properly, we need to do more work to account for all of these details. Also, I would encourage people designing tall buildings, anything above 40 levels in Indonesia, to get us to provide an assessment for wind noise, because wind noise can be generated in tall buildings through things like stack effects, type of construction of partition walls can cause a lot of nuisance for the occupants. If you use the wrong partition system, you can get a lot of creaking noise that you could have avoided if you use a different type of construction. These are the things that Windtech is a global leader in and can assist with those details. Perhaps we should have a special session on this subject.
Yeah. All right. Okay. Thank you. Another question: what is your opinion on the role of CFD, computational fluid dynamics analysis, for wind design?
Windtech does use CFD quite a lot, but not for structural or pressure studies. The turbulence models have not developed to a level that makes it feasible. And I think the important word is feasible. If you want to get anywhere close to the accuracy that you can get from a wind tunnel study. So it's not impossible, but in the Australasian Wind Engineering Society, we have made it not permitted because it's a very high risk. We see people attempt to use CFD, but to come to the same level of accuracy, you would have to simulate with a very powerful computer. One wind direction would take about 3 weeks, right? But if we say, yes, you can use CFD, you can end up with results that are very unreliable. You can be plus or minus 50% or more, just because the time step is not small enough, sample time is not long enough. There's so many requirements. Then the density of the mesh has to be very fine, that you can't use one of those simple turbulence models. You used to use something like a large eddy simulation turbulence model. There are so many, and each one of those has huge implications on cost. So we're talking about 10 to 20 times the cost of a wind tunnel study, and about 10 times the time to get similar accuracy. All right, so that's really what the limitation is, and so we're not really ready to engage. Anyone who tells you I can do this in CFD is really pulling wool over your eyes, and just be very careful.
Okay, well, I think that we're limited by time. I do have one question that I'd like to ask Dr. Tony. So with this, project experience that you've encountered, based on your experience, what when should and during the stage of design, when should the wind consultant be engaged to provide advice? And also based on your experience, we noticed that overall cost savings to the project is achievable as well, right? So do you have some sort of opinion on this?
Yeah, sure. Okay, so there are different aspects of the effect of wind on buildings. So the first aspect is outdoor pedestrian comfort. For that,
Hmm.
I think we can provide at least just a desktop or preliminary estimates right at the concept design. And that's very helpful because um, the thing you don't want is to go in and do a detailed design and then find, oh, we have a major problem here, and then you have to backtrack significantly in the design process. It's better to understand where the potential problems are right from the early stages of concept design. So I would encourage any building that's even notionally tall, at least address this problem. Okay, come to us, and it doesn't cost you anything, right? For us to give you some, uh, you know, pointers as to what to look out for. Okay, if you want a report from us, obviously we need to charge you something, but not much. Um, if if you are doing a building that's, say, as I mentioned in my presentation earlier, say 70 meters tall or more, it will benefit from a pressure study, but that's not needed at the early stages. So that's sort of, once you commence design development, that's probably the best time, and that's a very important value engineering exercise. If you're dealing with a building, say twice that height, say 140, 150 meters high, then again, as part of just in the design development phase. So we're talking about wind environment early on, but structural and pressure can wait until the design development phase. And then we're talking sort of up to about 150, between 70 to 150 meters. That could be dealt with right at the end. Much higher than 150, say, then maybe even higher than 200 meters, that the form of the building needs to be discussed also at the concept design stage, because that could have impacts on the efficiency of the structure, etc. The aerodynamic efficiency can start to have an impact. So maybe to sum it up, I would say any building, any notionally tall building could benefit from a wind environment input at the start. If it's substantially taller than 200 meters, at that same early phase, we can discuss building form for aerodynamic efficiency. And then at the design development phase, so once you've locked in all of the layouts of the apartments, the building envelope, then anything over 70 meters can benefit from a pressure study. Anything over about 140 or 150 meters can also benefit from a structural load study based on the wind climate in Indonesia. And not from the point of view of ultimate design for structural. I'm talking occupant comfort and serviceability. So ultimate design generally won't govern in Indonesia until you're significantly over 200 meters. So that's sort of ties in with the aerodynamic efficiency as well.
Okay. Well, it's 11. It's past 11:30 already, and I don't want to hold for the Friday's prayer. So I think it's a good time to conclude this webinar session. Again, you know, uh, we'd like let us thank Dr. Tony for his time and his knowledge sharing. Very informative session.
Yeah,
Um,
thanks to everyone for attending, and happy to assist if you need any input for your projects.
Baik, Bapak Ibu sekalian yang saya hormati, mungkin sekian acara webinar kita hari ini. Mudah-mudahan bermanfaat dan jangan lupa menjaga kesehatan dan selamat beraktivitas. Terima kasih.
Oke, terima kasih Pak Nik.